All right, team, we are looking at learning target 5 here, calculating rate of change, or essentially the slope of a graph. So because we know we're calculating, I did already pull up my Google calculator, so I had that ready to go. So have yours handy, split screen on your desk, whatever you need to make this happen. So the reason we're thinking about this in our current unit is one of our focus questions is, well, how can we use these data trends to model future changes? So we've seen changes to the earth because of warming and CO2 levels. We want to be able to say, well, okay, if this trend continues, what might we expect to see in the next 20, 100, 200, whatever it is years that we want to project to. So by looking at data like this sea level graph, what we can do is take a snapshot of what the current trend is and project that forward using something called rate of change. Right? So what rate of change is looking at is, well, how different is this data changing on average from year to year? So for this first one, sea level impact, I'm giving you here this rate of change. We're not calculating it, we're just using it at this point. So here we have a rate of change of 3.4 millimeters per year. So we're going to put that in here in our number 1, right? 3.4 millimeters, that's our unit, per year. So that's given to us. Well, how can I use that number, 3.4 millimeters per year, to predict, well, what might the change be in a 5-year time span? So remember, this number, 3.4, is telling us every year sea level is going up by that much. So if it's changing that much in 1 year, the math I want to do for 5 years would be 3.4 times 5, and then I would calculate that out to give me a 5-year change. So over here I've got 3.4 times 5. So I'm looking at 17 millimeters changing in the course of 5 years, right? I'm thinking about the 1-year change happening 5 times in a row to give me that formula and the calculation of 17 millimeters per year. And again, I can do that for any time frame. Let's do the same thing here for a 100-year span. If I know my rate of change, that doesn't change at all here, that stays the same. If I know my rate of change is 3.4, and I want to project, well, 100 years from now, what will that change be? Again, I'm back over here in my calculator, 3.4 times 100. So rate of change for a 100-year time span, I'm looking at a change of 340 millimeters over 100 years. And that is roughly plus or minus just a little over a foot, okay, on this current projection. So how can we do that whole thing on our own? Where can I get the rate of change from? If I'm given a graph like this, doesn't have the rate of change, I need to calculate that first before I can do any projections. So we have to find 2 points on the graph, and this is the important part here, that use a current trajectory. I need to choose 2 points on the graph that are going to most accurately represent what the data is doing now. So my recommendation is to try to find the most recent span, somewhere between 5 and 20 years, on your graph. So for this particular one right here, I wouldn't want to use these 2 points, right? 1, they're not very recent, and 2, they don't match to the current trajectory, right? Currently, we can see the graph is increasing. So using these 2 data points isn't going to give me that trend that I can project forward. I want to use something more in this area. And I'm going to stick, this says 5 to 20. I'm going to go with 10 for this current example we'll think about here shortly. Once we have those points determined, then we need to do a little subtraction. So we're essentially finding the difference between our two x values and the difference between our two y values. And once we have those subtractions, we're dividing to get that overall rate of change. So you're going to get the change between the y, change between the x, and do a division. So let's go for it. Again, we got our directions right here. First is to pick 2 points, current trajectory. Like I said, I'm going to stick within 10 years. I could easily go 15, to a midpoint, but I'm going to stick with what I can on the graph. So 2010, 2020 are really easy to read, so that's what I'm going to use. So the first value for y I'm going to use is 2010. And that's my first value because it happens first on the graph. And for 2010, here's my data point. And I carry that over, and you can use that line tool on Notability. That y value is 11 tropical storms in 2010. I want to do the same thing here for 2020. I'm going to use this projection up here. My y value is 2020. And pulling over to this side, a little bit above 15. I'm going to go 15.3. So far my data says that in 2020, there was 15.3 tropical storms. In 2010, there was 11 tropical storms. I want to figure out the average rate of change in that 10-year span. So I first need to subtract them. 15.3 minus 11. So that is a change of 4.3. And I'm going to divide that by my change here from 2020 to 2010, which is, of course, a 10-year change. So by dividing that, I will get my rate of change. So I've got 4.3 divided by 10. So my rate of change of tropical storms is 0.43. So what does that mean? That means that every year there's about 0.43 tropical storms per year. Again, that's an average, right? I can't really have 0.4 of a tropical storm, okay? But on average, it's going up half or so of a tropical storm per year to get me where I'm at. So that's my rate of change. So I need to use that moving forward. So my rate of change for tropical storms is 0.43. And check your notes there. I think I had a little typo. It should say tropical storms. And I'm projecting here to the year 2050. So how many years away am I projecting? Well, the difference between 2020 and 2050 is a 30-year span. So in order to get my projection of how much the tropical storms will change in that time, I need to do, again, my calculation. 30-year change of changing 0.43 tropical storms per year (30 times 0.43). That means we're going to see an increase of 12.9 tropical storms over the next 30 years. So the next 30 years will continue to increase 12.9 storms. Which means in 2050, if there's 12.9 more storms, how many will there be total? We're looking at an increase of 12.9. In addition to the current levels, 2020 where we left off, which was 15.3, 12.9, plus 15.3. That means in 2050, we can expect approximately 28.2 tropical storms in that year, if we continue to increase at this rate of about 0.43 tropical storms more a year. This will be the increase in the next 30 years, in addition to where we're at now, so the total amount will be 28.2. So you should be able to try this again on your learning target number 5. I'm going to pull that up here and just kind of show you the info. Learning target 5, ready to go. Here we are, same idea. So again, pick a location for your X value that is both recent, 5 to 10 years, 5 to 20 years, and shows the trend. So I would just stick with a nice easy spot to read on the graph, 2000 and 2020, right? You can get your 2 points right from here. Subtract those two values, y and x, figure out that rate of change. And calculate out for that total increase in 2050. As always, reach out with questions.